Greetings, JP Astro Guy here. You know, in the eastern area of Japan in the summertime, the weather is very unstable and it changes so quickly and you get so many cloudy days. It's been difficult to get out, but there's been little pockets of opportunity that come up every now and then, but you got to be ready to jump on them. I mean, literally, the forecast was to be cloudy all night up until about 5 hours ago, and now they're saying 5 hours worth of clearing tonight. So I'm out here again on top of Kawawa Fuji, this lookout area near my house. See one of my previous videos for an explanation about this place. But tonight I'm going to do a little bit of imaging, but I'm really going to focus on trying to get a better understanding of polar alignments. I'm kind of fascinated with it and trying to really determine what the accuracy is of this AM5 mount with this ASIAIR Pro. So I'm going to run a series of them and I'll share that data with you. Also, if you recall in my last video, I was playing around with the AM5 mount to try to see if I can do some unguided imaging on the stars. And I proposed that probably 60 seconds would be fine. Well, I'm going to test that out tonight with some nebula imaging. So we'll run non-guided exposures on some nebula, and hopefully in the next half hour or hour, the skies will clear as they forecasted, and we can get started here. Thanks for joining me. Stick around. So first of all, as you can probably tell, on this second attempt now at this experiment, I did not go back to Kawawa Fuji Park. You can see how windy it is tonight. I think we're up to like 20 kilometers per hour coming from out of the south that's going in this direction. Hence, I got the wind barrier up, and this is really the best place to do astrophotography when it's windy. So I decided to come to this park, which I also filmed. I think it was Bubble in the Park was the previous previous YouTube video that I made right here on this spot. So I started my investigation by doing polar alignments against the North Celestial Pole. As you may know, this is not something that I can do from my backyard. As usual, I set up my tripod and mount and used an iPad compass application to align it about 8 degrees east of the magnetic north. As I explained in the last video, this corresponds to the direction toward true north from my location in Asia. Of course, when doing a polar alignment with the ASIAIR Pro Astro computer, an initial photo was taken through the main OTA, plate solved, and hence a reference location is created. After that, the mount automatically turns on its RA axis, rotating 60 degrees counterclockwise when facing the stars. The computer has the complete image of the night sky in its memory and hence can predict what the star pattern should look like if the mount was perfectly polar aligned. A second photo is taken after the rotation and plate solved. Of course, the second image will not exactly match the predicted star pattern because the mount is not perfectly aligned. By digitally mapping these two images to the sky map, the ASIAIR then knows the precise misalignment of the mount relative to the North Celestial Pole in both declination and right ascension. It provides this information to us and allows adjustments to be made, after which another photo is taken. This new photo is remapped to the sky map, and we continue the process over and over until our physical adjustments finally zero in on a precise alignment. When this is achieved, we get a smiley face indicating success. It is okay to continue to fine-tune the mount alignment down to better and better arc seconds of accuracy if that is indeed desired. In my first polar alignment, I achieved an accuracy down to only 29 arc seconds of total error. After this, I repeated the North Celestial Pole polar alignment a total of 10 times. After completing the alignment, I simply instructed the mount to return to the home position, and I repeated the same polar alignment process over and over and over again. Each time I saved the data for later analysis. And here's the data that I collected for the North Celestial Pole polar alignment. I also took a screenshot before the rotation on the very first alignment and the last alignment, and those images are shown below. The difference between the data point -1 and 1 is that I again manually adjusted the RA and depth axis, trying to exceed 29 arc seconds. Actually, that turned out to be stupid because I could not realize that accuracy again and settled instead for 57 seconds on polar alignment number 1. But then, from number 2 until number 10, there were no physical adjustments made, just a return to the home position and a repeat of the polar alignment routine to observe the alignment numbers. I am sure you can see for yourself the astounding reproducibility of the mount's movement, each time coming to within 1 or 2 arc seconds of error from the previous run. We finished the North Celestial Pole polar alignment, and despite of sort of the high clouds, the accuracy of the polar alignment just blew my mind. I mean, if you haven't, hopefully you've seen the data already. I mean, it's just crazy how accurate it's sort of, we get those readings and come back to home and go back to the exact same spot over and over and over again. It blew my mind. This next slide probably has no intrinsic value, but I wanted to show you where the field of view ended up after the 60-degree RA axis rotation. Shown is the home position star image and the 60-degree rotated star position image. I noticed this bright star in the upper right-hand corner of the field that I suspected was Polaris. So I took that image and uploaded it to astrometry.net for plate solving. Sure enough, it came back with a verification that the bright star was indeed Polaris. Now, as I reported in my last video, I have not been that successful with the all-sky polar alignment. So we're going to try that next. But I don't have much room here, so I'm going to try to pick a starting point somewhere in that direction over there. So let me navigate this AM5. We have the experimental feature for all-sky polar alignment selected here. That looks good. And I'm in the polar alignment window here. So I don't know if you can see, but I lined it up a little bit more angled to the left here. And over my right shoulder is a very bright star, which is actually Mars rising in the east over there. So let's try this and see what happens. So this is still polar aligned from the North Celestial Pole polar alignment. So it really should be pretty close. As you can see, it's at 9 minutes error. So that's quite different than what we were getting with the North Celestial Pole polar alignment, and I didn't touch the setup at all. So let me align this and get it with the smiley face, and then we'll repeat it multiple times. Okay, I just took 2 readings, and you can see they differ a little bit. I'm going to bring it back now to position close to where I was before and repeat this again. Maybe we'll go a little lower this time. We'll try this again. 3rd attempt here. We're at 1 minute and 37 seconds. And now let's see what happens in the next attempt. All right, let's go. We're 3 minutes out now, and we're out of the smiley face. Well, let's keep going. Do it again. Why don't I start high this time? Start around there this time.
For your information, this is the top half of my AM5 periodic error test report from ZWO. The repetitive periodic error for my mount varies from 8.6 arcseconds to 22.1 arcseconds total deviation. I think this is about average in terms of specifications for the AM5 product line. Now, similar to the previous way I displayed the data with the north celestial polar alignment, I have also shown the total alignment error statistics for 9 consecutive all-sky polar alignments. Here I converted all the values into arcseconds only. Actually, I had done 10 polar alignments, but somehow forgot to take a screenshot of the data for one of them. On the bottom, I also graphically plotted out the values for each declination and right ascension data point for every polar alignment in arcseconds. Immediately, I am sure that you noticed that the all-sky polar alignment process shows much greater deviation than the north celestial polar alignment process. Let's take a closer look at all the data on the next series of slides. Starting with the all-sky polar alignment data, it is obvious there is some kind of random drift in the numbers reported for the declination and RA values. The column named total also comes from the ASIAIR reported values. I suspect this number represents a straight line hypotenuse value from the true north celestial pole directly to the misalignment point. You know, if the deck represents one point and the RA represents another point and the NCP represents a third, then the deck values squared plus the RA values squared equals the total value squared. I suspect this is how the total number is actually calculated. Regardless, if you look at the change in values of the total from alignment 1 to alignment number 2, for example, you can see the difference is 84 arcseconds. The column labeled drift represents the difference in absolute value from the immediately previous alignment value. Drifting up or down is irrelevant. It is the change that matters. If I take the average of these drift values from 8 to 114, that number is 46 arcseconds. Now, let's compare this average total drift value to the north celestial polar alignment value. That value for the NCPA is actually less than 1 arcsecond. The numbers range from 0 to only 2 in absolute values. And finally, let's look at these total drift numbers graphically displayed. There appears to be more than 50 times greater drift in the all-sky polar alignment values. So why the big difference? Well, again, this is just my interpretation, but I think the north celestial polar alignment values are an indication of the precision engineering of the AM5 instrument. It is absolutely capable of arcsecond reproducibility in mechanical movements. Personally, I did not expect this level of precise engineering. I think it is rather remarkable. Perhaps, if I continue to repetitively do this alignment process more and more, I might begin to see the periodic error be introduced, which for my mount is about 8 to 21 arcseconds. But this did not seem to be evident in this experiment. I think that might be because the periodic error occurs over longer periods of time, and my experiment lasted only 16 minutes from alignment number 1 to alignment number 10. Again, that is just speculation. I do a lot of that. The all-sky polar alignment process also only rotates on one axis, the same RA axis, so the precision in movement must not be a factor. We now know it is precise. The lack of reproducibility might therefore be related to data interpretation, something less reliable in the algorithms. That is certainly one possibility. So, based on this data, I decided the best course of action to do unguided imaging of any celestial object might be to use the North Celestial Pole polar alignment process. In my last video, which I did at my house in the backyard, I used the all-sky polar alignment process. If you recall, in the 60-second exposures of the M39 open cluster, I claimed that the stars appeared to be round and no trailing was evident. Well, a few viewers challenged me on that statement, pointing out that the stars were not perfectly circular, but rather slightly oblong. On review and close inspection, I cannot argue with that. Some stars did appear slightly obtuse, but on a larger full-frame image, I certainly could not tell. So in this video, I will make no definitive claims. I will let you make your own assessment. And instead of a star cluster, I decided to image a bright nebula target to again check for star trailing when taking unguided photographs. But before all of that, I went back to the home position and I did an excellent North Celestial polar alignment with a total error of only 18 arc seconds.
I'm going after the Cygnus Wall and part of the North American Nebula, but at the moment we're taking a little bit of a break because some mid-level clouds have rolled in, but I think I already got about 10 to 12 exposures already completed. I hope to get about 45 minutes to an hour using 60-second exposures with this AM5 mount at 448 millimeter focal length with my ASI 533 camera. Now I'm not doing any guiding, and that's the point of this, is to look at the quality of these nebula photographs without guiding. Perhaps if I have additional time and the clear skies hold out, I can try 90-second exposures and see how that works.
On this night, again, clouds were a problem. My imaging was from about 11 p.m. until midnight, and during that time having to dodge very fast-moving mid and high-level clouds. It was warm and humid and windy, but my wind barrier and the stability of the AM5 mount worked outstandingly. I am sure that some of my subframes did have a bit of cloud interference, but I used them anyways. I got 41 subs at 60 seconds, but only 7 frames at 90 seconds. So the quantity and quality of the data I collected was not very good, but I processed it anyways. These are clearly not my best images, no thanks to the weather, but they turned out much better than I expected, so I am sharing them with you. To look closely for star trailing, remember I am not using guiding, I randomly selected and magnified 8-star regions from all around the final processed 60-second image. They are shown here. I would say some of them are not perfectly round, but not more than a few pixels off from being perfectly circular in my opinion. Now, let's look at the 90-second data. Oh, by the way, all these nebula images are taken using the Optilong L-Extreme filter. The 90-second processed photo is only 11.5 minutes of total integration time, so one cannot expect much detail in the nebula. And on this slide is a comparison of the 60-second image and the 90-second image. At this 533 MC Pro camera full image resolution, the stars look pretty similar. Here are 2 single-frame screenshots from the ASIAIR menu that I magnified to look for star trailing. I adjusted their sizing to try to show similar fields of view on this slide for comparison purposes. And finally, from the processed images, I magnified 4 different star images from the 60-second photo shown in the top row and from the 90-second photo shown in the bottom row, from exactly the same regions. Perhaps you can see the stars are becoming a bit more oblong, stretching toward the upper right corner of the photo. But still, this shape is only noticeable when examining the photo after significant magnification. Now let's summarize. With respect to the ASIAIR polar alignment feature and its precision and performance in concert with the AM5 mount, I have to say that the North Celestial polar alignment feature is outstanding. It totally blew away my expectations. If you want highly reproducible polar alignment, you should absolutely use the North Celestial polar alignment procedure. It seems to have mechanical precision and repeatability down to just a few arc seconds. But reproducibility and precision are not actually the same as accuracy in polar alignment. I can only assume it has high accuracy as a result of the mechanical precision and good plate solving, but I actually have no way to test this. As for the all-sky polar alignment procedure, by my estimates, its repeatability is within 1 to 3 arc minutes due to random drift in the RA and deck numbers. It appears to be more than 50 times less accurate than the North Celestial polar alignment procedure. In this case, lower reproducibility inevitably means less accuracy. But from experience, we all know that a few arc minutes of error is easily corrected by constant guiding, and hence this level of polar alignment accuracy is adequate for deep sky astrophotography. I have taken some beautiful nebula images after all-sky polar alignment while using guiding in my tiny backyard. And frankly, for most deep sky imaging, I generally will employ guiding if I can. At this point, I should point out that clearly ZWO recognizes this all-sky polar alignment process is not ready for prime time. On the latest firmware update, it was still part of the experimental features section in the ASI menu system, so I suspect it is still work in progress and will eventually be improved and released as a standard feature in the future. At least, I hope so. And then, regarding unguided imaging, with my imaging trained setup at 448mm focal length and the small sensor size of my ASI 533 MC Pro camera, I am photographing about 1.45 degrees of sky. Personally, I consider this to be rather mid-range for astrophotography and not wide field. That is my opinion. At this level of magnification, when viewing a 60-second exposure of the entire image, I cannot see any trailing or oblong shapes of the stars. Now, I am an amateur using somewhat low to mid-range equipment, and my tolerance for imperfections is probably fairly high, but in my opinion, I think that unguided 60-second images at 450mm focal length using the AM5 mount can give acceptable results. Having said that, I highly recommend that one should use the ASIAIR North Celestial Polar Alignment procedure to maximize your image potential. Now you have seen the data. You make your own conclusions. Do you think my unguided image of the Cygnus Wall and the star patterns demonstrate acceptable precision to you? For me, I am quite happy with the image, especially for only a 41-minute exposure with some cloud interference. Well, I hope this video gives you a better understanding of the capabilities of the AM5 mount. With this video, I am done with my practical assessment of its performance. This diversion to a product evaluation for me was fun, but not completely in line with the chosen adventure theme for my Astrophotography Japan YouTube channel. I promise to get back to that theme in the upcoming videos. Oh, by the way, since there was little to no Japan content in this video, I included a bit at the very end, simply for your amusement. Consider it a celebration after imaging. In the meantime, I want to wish you clear skies, and I sincerely thank you for your support of Astrophotography Japan. My name is Paul Cheesegel, and I am an astrophotographer.
Hey! はい、今度はネイマールでやってみましょう。